Hello everyone, I'm Hongbo Bo from University of Bristol, and I'm happy to be here to share with you about our recent work, Social Network Influence Ranking with Embedding Network Interactions for User Recommendation. It is a joint work with Ren, Jun, and Wei Ru. I'm going to show our work from this file following contents. The first one is the introduction part. Due to the everywhere and scale of digital social networks, there has been significant interest in understanding the mechanisms of their formation and growth. For example, in understanding the role of social influence in online social networks. Social influence is a crucial factor in many aspects of life and society. Due to social influence is a very abstract concept, academic research tries to quantify the influence value. The quantification of influence can be applied in the studies, like propagation of ideas, behaviors, and economic outcomes. Our work is to design novel methods to overcome the drawback of current methods. In our study, we will consider, without loss of generality, the social network, Twitter. Twitter permits non-reciprocal connections, whereby it is not uncommon for a user to be non-reciprocally connected to a vast number of other users. One common way of measuring influence between two users is by observing the likelihood that one user reads the other's tweets. On the other hand, interaction information has been shown to be an important indicator of influence among users. On Twitter, these interactions may include mentioning another user, liking a tweet, retweeting a tweet, or replying to a tweet. This could be considered as a strong indicators of influence as they clearly show the reaction of users to tweets. For example, the retweet interaction can be considered as an intent of users to amplify or further diffuse the original tweet, thus potentially increasing the influence of the original tweet. We study how we can assign influence values to users in a social network. We are particularly interested in how the integration of interaction information into an influence measure can lead to a better measure of influence. We first embed the nodes into embedded spaces. An embedding is a mapping of a discrete variable to a vector of continuous numbers. There is an example of an embedded space. The input graph consists of 9 nodes and 11 edges. After embedding, these 9 nodes will be presented in embedded space as 9 vectors. These vectors will remain the topological information of the original input graph as much as possible. And then we can utilize the methods of dealing with the vectors to deal with the nodes in a graph. Then we define a closeness measure which measures how close users are within the embedded spaces. After that, we assign the transition probabilities between users in a social network. In the last, we used a PageRank-like approach to assign an influence value to each user. Once user influence has been modeled, it may be used for tasks, such as user recommendation. We evaluate the performance of our proposed influence ranking algorithm with a standard recommendation task. In this case, recommending user to follow on Twitter. Then allow me to provide the preliminary of our study. A Twitter network can be represented by a graph G which consists of node set V and edge set E, where V represents Twitter users and E is the set of directed edges, representing how the nodes are connected. The following graph is a directed graph which represents the users and the following relationship among them. There's an example of Twitter following graph. As we can see, the user A follows user B, B follows C, and user A and C follow each other. We use node-to-vector in our method. Node-to-vector learns a feature representation for nodes in a graph. The algorithm samples the node sequences by using a random walk and then extends the skip graph model into the graph domain in order to model the conditional likelihood of each node and its neighborhoods. For each node in the graph, the objective function maximizes the probability of observing neighborhood nodes in the feature representation. We also use the PageRank algorithm. It is first proposed as a web page ranking algorithm, which can quantify the importance of web pages based on the links between them. And the PageRank value of a node is calculated as follows. Pi is the node we want to calculate, and Pj is the node who can link to Pi. M is the set of all nodes who can link to Pi. Alpha is a damping factor which is usually smaller than 1, and N is the total number of nodes in the graph. The calculating process is an iteration process. When the entire process achieves stable, the PR values are the importance of web pages. There is an example of PageRank. The sets of the nodes are PR values. The nodes with yellow color are web pages who have ingoing links, and the nodes with green color are the web pages who only have outgoing links. After PageRank process, we can see the sets changing. Web pages B and C are the most important pages, and these green web pages are not important. In the following part, I'm going to introduce our method. Our definition of influence is based on the following intuition. If a user is both followed and interacted with by many users, then we consider this user to be influential. And if a user with a high influence value follows another user, the influence value of the user being followed will increase accordingly. Inspired by PageRank, if the influential user follows number m users, the contribution the user provides to another is his influence value divided by m. This follows the PageRank assumption that each following relationship has equal strength. Our core idea is that if a user follows another user with active interactions, then the user's contribution to another user's influence should be higher than the default contribution of 1 out of m. We build 4 kinds of interaction networks on Twitter: favorite, mention, reply, and retweet. An interaction graph is a weighted graph. There are examples of 4 kinds of interaction networks. In graph A, favorite interaction graph, user A likes user B's tweets 3 times totally. In graph B, mention interaction graph, user A mentions user B 3 times. And in graph C, reply interaction graph, user A replies user B 3 times. In graph D, retweet interaction graph, user A retweets user B 3 times. Based on our definition of influence, we define a closeness measurement to quantify how close a pair of users are, with a closer relationship causing an increase in the contribution of influence. More specifically, The closeness measurement is defined based on the extent of different types of interaction between users. The weight of edges in interaction graphs is a simple method of representing how close a pair of nodes are, but it is less able to measure the relationship between unconnected nodes. Therefore, we proposed to use a node embedding method, node-to-vector, to map the graph nodes to a vector space where the relationship between embedded nodes can be easily calculated. We considered four vector spaces: favorite, mention, reply, and retweet spaces, which are the mappings of the four interaction graphs by node to vector. For each node, the representation in each vector space is a d-dimensional vector. A common method to measure the closeness in a vector space is the Euclidean distance. The Euclidean distance between P and Q is calculated by this equation. In this equation, d is the vector dimensions. We account for this in our closeness measure over all the four embeddings for a single use as follows. The lowercase letter ci is the closeness between user P and Q in one space, and the uppercase letter c is the total closeness between these two users P and Q. In our setting, given a pair of users P and Q, where Q follows P, Q's contribution to P's influence value is calculated as Q's influence value divided by the number of Q's outgoing edges. In addition, because a user Q may have different degrees of closeness to each of its followees, the extent of influence Q contributing to each of its followees is different. In order to calculate the influence of users on Twitter, we propose a PageRank-like algorithm which called EI-rank. EI-rank visits each user with a transaction probability by following an appropriate age. The transaction probability from user Vj to Vi is defined as this equation. With the transaction probability, the influence value can be calculated as the equation, where M represents the set of nodes that are incident to nodes Vi. Alpha is the damping factor between 0 and I to prevent the random walk following the loop edges and getting stuck in sinks. And N is the total number of users in the following graph. Through an iterative approach, the algorithm propagates the influence along the edges of the graph to reach a stable state. The EI rank value at convergence is the influence value of each user in the following graph. But why we need to calculate the closeness? If we use the weights of edges in interaction graph to calculate the transition probability from user A to user C, the answer is 0, even though there is a following relationship from A to B and B to C. However, when our proposed method, the transition probability from A to C after embedding is 0.449, which is more reasonable than 1. The following part is our experiments on Twitter. By using the Twitter API, we collected data as follows. We seeded our collection with the 100 users who have the most Twitter followers. We then collected their followers, resulting in a dataset of more than 14,000 Twitter users. To build interaction graphs, for each user, we collected up to 500 of their most recent tweets and favorite tweets. The statistics of each graph are shown in table. For each following relationship, Let SO and SF be the followee and follower respectively. We randomly chose 10 Twitter users, donated as S1 to S10, who have no direct connection to SF, and then remove the true age between SF and SO. There are 10 unconnected Twitter users and 1 true followee. So out of the possible 11 options, our assumption is that SO shall be ranked the first in the ranked list of recommended user to follow. That is, SO should have the highest influence. To gain a better understanding of the performance of different network configurations and settings, we use different sampling strategies to select different sampling sets for selecting following relationships, and evaluate the algorithm's performance when dealing with different contexts of following relationships. In total, we have designed 4 sampling strategies. Strategy 1. Randomly sample n existing following relationships from the entire following graph. Strategy 2. Select the top 10% of users who have the most following and randomly sample n existing following relationships among them. Strategy 3. Select the bottom 10% of users who have the least followers and randomly sample n existing following relationship among them. Strategy 4. Choose the top 5 largest communities and sample n existing following relationship from each of them. In each case, we retrain our model with the true age removed and we set n to 30, damping factor to 0.85, weight to 1 and dimensions to 64. The figure shows the results of each approach with different strategy. As can be seen from the results, in all scenarios studied, our proposed algorithm EI rank performs better than Twitter rank, as it on average ranks the true follower higher on the list. We further evaluate our algorithm on the individual components of our approach, namely PageRank and node-to-vector, in which our proposed method shows the best performance in 3 of the 4 experiments. For strategy 4, we show the average result based on ranking influence within communities, rather than the entire graph. The statistics of communities are shown in the table. Here, it is clear that our method performs the best on average across all communities, with the highest ranking for the true user, as well as the smallest standard deviation. If we look closer into the community, as shown in this figure, EI rank has consistently the highest performance across all communities. Performance of our method when applied to different network samples based on percentiles of follower counts. We select 30 existing following relationships from network configurations where we sample from the top 5%, 5% to 10%, 10% to 20%, 20% to 30%, and 30% to 50% of all the follower counts of the users. Respectively, we also conduct a similar experiment by sampling from the top 5%, 10%, 20%, 30%, and 50% of follower counts. The figure shows that influence becomes more difficult to measure when considering users with less followers. As we consider a global influence measures, the farther we move from the more influential users in the network, the more difficult it is for us to accurately model influence for user recommendation. Then allow me to summarize the conclusion of our work. We first proposed a method for calculating how close nodes are based on the embedded interaction networks. We then proposed a PageRank-like method that utilize the closeness method to model transaction probability that capture influence propagation on a social network. We then evaluated our social network influence ranking method in the context of user recommendation on Twitter. We studied the ranking of the true followees across a range of experimental settings. By selecting the user with the highest influence as the recommended user to follow, our experimental results show that influence ranking for user recommendation typically performs well.